All right, I just finished talking about NOx catalysts. Now it's time for CO catalysts, which they are kind of similar, but kind of not really. So, okay, so what does a CO catalyst do? Its goal is to convert CO into CO2. How do you do that? Well, the only thing you're missing is more oxygen. So you just add oxygen. And where are these typically used? Well, the CO catalysts are typically used in like a car, like literally in your car's exhaust, there is a CO catalyst. And like also just big engines and whatever. Easiest use case is your cargo. And it's great because it doesn't need anything. You don't need to add more oxygen because your car runs fuel lean anyways, so there's already excess oxygen. So you don't need to add anything. You just put the catalyst in the car, in the exhaust, and it's fine. So how does it work? Well, these catalysts, the CO catalysts, are made of platinum or palladium. Where are those? Or rhodium. Platinum, palladium, rhodium. Doesn't really matter where it is in the metal group. All it matters is that it's a metal, so it's super polar. So you have over here I drew a lattice. For this demo, it'll make more sense if I just draw a tube. So you have your tube with a couple platinum atoms. Let's just call them platinum. It's the same if it's rhodium or whatever else, but let's just call them platinum atoms. So what happens? So you've got your CO and your O2 coming in. And then the idea is that the platinum, well, okay, what are the charges on these? So O2 is, let me look at my notes. Well, okay, technically, I kind of messed up here a bit. So there's O2, but there's also like after combustion, and frankly, in air normally, there's also, this is why I should have reviewed my notes before I started recording. That's okay. There's also just free oxygen atoms as well. Just free oxygens floating around. That's like, that is in air, but it's especially in air if it's in combusted air. So there's free oxygens as well. So the charges on these are, oxygen is -2. This is O2, which is 0. And this is CO, which is -4 and -2. Would it be -2? I think it would be, or it'll be +2 or something. I think it's +2, because if you add another oxygen that's -2, then it's CO2, and yeah, okay, I think it's +2. So, okay. So you got these flowing through here. The idea is, after enough of these molecules have flowed through, and like a lot of them flow through because it's a freaking car, and it outputs a lot of molecules. The idea is the O2 will get attracted to the PT, which is like a, maybe it's a +4. Let's assume it's like the most extreme case. +4. It'll get attracted to these and it will stick on them. So you have O2 and you have O2. Not a O2, just a O. because the O2 isn't attracted to anything. The O2 will just flow through here. But you got some of these with free oxygens on them that get stuck on them because it's polar, and it'll pull them towards them. So the idea is once enough of these are like filled up, then as the CO travels through, it will, statistically, it will bounce off enough of these, and one of these will break free, and then it'll become CO2. CO2. I don't think I did the best job of explaining that, but the idea is there's like 1 million of these PTOs, and there's one CO molecule, and if it bounces off of enough of them, eventually it'll just knock off one of the O's, one of the oxygens, and then it'll merge with it, and it'll get out of here. So that's great. Now, there are a couple ways this stuff can go bad. Like a catalyst can stop working. I didn't go over that for the NOx catalyst, but let's go over that here. So if there is another polar molecule, it could just clog up the catalyst. For example, let me look at my notes. I think sulfur, maybe? Yep, sulfur poisoning. So if there's sulfur, which, like if you're driving at the beach and there's salt in the air, I think that's one of the causes of sulfur. But you can also get sulfur in fuels because it does get pumped up in the crude oil from underground. So there is sulfur. Usually it's not that much of it, but there is some. So if there's sulfur right there, it's also a -2. So it's the same as oxygen. So what can happen is if there's a sulfur, it can go in and it'll take up one of the spots that oxygen would have taken up. And then that means that oxygen can't go there. But an oxygen can, let's say an oxygen is there and a sulfur is there. The CO will come by, it'll hit this, it won't get it because it doesn't need it, and it'll come over here, get the oxygen, and then leave. But nothing will get the S. The CO won't get it, this oxygen won't get it, another sulfur won't get it. Maybe it will, I don't know. But the idea is that it won't. So that sulfur is just gonna stay there forever. And if that happens over here, if it happens over here, then you've lost half of your catalyst efficiency. And if that happens to all of them, then your catalyst won't work anymore. So sulfur poisoning is big. And frankly, it's not just sulfur, it's literally any other free polar molecule that's floating through here. That is the idea. Basically, statistically, if CO bounces off enough of these platinum molecules with a free oxygen attached to it, chances are it'll knock one of them off and it'll keep it and turn into CO2. But it can get poisoned by other polar molecules. If a polar molecule takes its place and nothing wants to react with it, it'll just stay there forever and poison it, as in the CO catalyst just won't work anymore. Cool. I think that's literally it.